towards this session, we shall first begin with a small introduction to SciPy and the difference between NumPy and SciPy. Following that, we shall take a look at the sub-packages present in SciPy and then take a deeper look at each of them, starting with basic functions, followed by special functions, integration functions, Fourier transforms, linear algebra, and interpolation functions. So I hope everyone's ready for this. Just give me a quick confirmation in the chat box, guys. Okay, great. I see many of your responses. So let's move on towards the first topic, which is what exactly is SciPy? SciPy is an open source Python library which is used to solve scientific and mathematical problems. It is built on NumPy extension and allows users to manipulate and visualize data with a wide range of high-level commands. As mentioned earlier, SciPy builds on NumPy, and therefore, if you have to import SciPy, there is no need to import NumPy. So now you'd be wondering, what is the difference between NumPy and SciPy? Both NumPy and SciPy are Python libraries used for mathematical and numerical analysis. NumPy contains array data and basic operations such as sorting, indexing, etc., whereas SciPy contains all the numerical code. Though NumPy provides a number of functions that can help resolve linear algebra, Fourier transforms, etc., SciPy is the actual library that contains full-featured versions of these functions. However, if you're doing scientific analysis using Python, you'll have to import both the NumPy and the SciPy libraries. Okay, so now let's move on and take a look at the sub-packages present in SciPy. SciPy has a number of sub-packages for various scientific computations. As you can see on the screen, the cluster sub-package is available for clustering algorithms. Constants deals with physical and mathematical constants. Similarly, FFT pack is for fast Fourier transform routines, integrate for integration and ordinary differential equations, interpolate for interpolation and smoothing splines, etc. For a detailed description on each of these, you can follow the official documentation. So now let's move on and take a look at the basic functions that you can use over here. Since SciPy builds on NumPy, you can make use of NumPy functions itself to handle arrays. To know in depth about these functions, you can simply make use of help, info, or source functions. The help function returns information about any function or a keyword or class, etc. Now this function can be used in two ways. One is without using any parameter, and the second is using a parameter. I'll be showing both these methods to you in a while. Similar to the help function is the info function. This function also returns information about any function or a keyword, class, etc. The source function, on the other hand, returns the source code only for objects written in Python. This function does not return useful information in case the methods or objects are written in any other language. So now let's move on towards a Jupyter notebook and see how you can make use of these functions. Okay, so first let's take a look at the help function. Like I've already told you all before, the help function can be used in two ways. One is by supplying a parameter, and the second is to use it without any parameters. I'll be showing you all both these methods. One thing I want you all to note is that all sub-packages present in SciPy need to be imported exclusively prior to using them. So in case I have to use the cluster package, I'll have to import it exclusively from the SciPy library. So for that, I'll have to type from SciPy import cluster. And then I'll hit run. Okay, so now making use of the help function to retrieve information about this sub-package. All I have to do is type help, and within that, type cluster and hit run. So as you can see, all the necessary information about this sub-package has been returned by the help function. So now, if I want to use the help function without passing any parameters, all I have to do is type help and hit run. So as you can see, it's asking me to enter the name of any module or a keyword of which I want to retrieve information. So here, I'll just type scipy.cluster. So as you can see on the screen, it has returned all the necessary information about this sub-package. Now, in case you want to stop this function from execution, all you have to do is type quit and hit enter. So now, if I want to use the info function, all I'm going to do is import SciPy and then type scipy.info and pass the name of the package as cluster. Now I'll hit run. So as you can see, this function has also returned the necessary information about this subpackage. Same is the case with the source function. All I have to type is scipy.source and pass the parameter as cluster. Please make a note that every time I'm using the cluster keyword only because I've imported this package. If I use the name of any other package without importing it, it's going to throw an error. So now I'll hit run. Okay, so I hope you've understood how these three functions work. Okay, so now let's move on towards the next topic, which are special functions. SciPy provides a number of special functions that are used in mathematical physics. These functions can be anything such as convenience functions, gamma functions, beta functions, etc. In today's session, we'll take a look at the exponential and trigonometric functions which are present within the convenience functions. SciPy provides two functions using which you can compute 10 power x or 2 power x, where x can be any integer. Okay, so now let's jump onto our Jupyter notebook and see how these functions work. So the first thing I'm going to do is create a heading over here. And I'll name this as special functions, or I'll just say special. Now I'll have to import this package from the SciPy library. So I'll use from SciPy import special. After this, I'll take any variable, say a, and I'll type special.exp of 10, which is to compute 10 power x. And for the value of x, I'll write 2, and then I'll just print a. Sorry guys, I had to type special.exp of 10. So as you all can see on the screen, this function has returned the value for 10 power 2, which is 100. Similarly, if I have to calculate the values of 2 power x, I can make use of the exp2 function. So all I'm going to do over here is take another variable, say b, and then I'll type special.exp of 2, and the value I'll pass as 3. Then I'll just print b and hit run. So as you can see, I've got the output for 2 power 3, which is 8. SciPy provides a number of functions that deal with trigonometry. Using these functions, you can calculate anything such as sine, cos, tan, etc. So now let's get back to our Jupyter notebook and see how this works. Okay, so I'll take another variable, say c, and then I'll use the sine theta function over here. I'll take another variable, say c, and then I'll calculate the sine value of 90 degrees. I'll use the sine dg function, and I'll pass the value as 90. After this, I'll just print c. As you can see, the sine value of 90 degrees is 1. Similarly, you can also use the cos dg function. So I'll just change the name from sine to cos over here and then hit run. Okay, so as you can see, it has returned the value for cos 90. So I hope everyone's clear till here. In case you have any doubts, please do let me know in the chat box and my team is here to help you. So now let's move on and take a look at some of the integration functions that are present in SciPy. Integration is a way of adding slices to find the whole. It can be used to find areas, volumes, central points, etc. In today's session, we'll be seeing how to solve general and double integration problems. SciPy provides a function named quad that can calculate the integral of a function which has just one variable. The limits can range anywhere between plus and minus infinity. So now let me jump onto my Jupyter notebook and see how this function works. I'll just create a heading over here. So before I make use of the quad function, I'll have to import the integrate submodule from the SciPy library. And to do this, I'll type from SciPy import integrate. After this, I'll use the help function to retrieve information about the quad function present in the integrate module. As you can see over here, it has returned all the necessary information about this function. The quad function basically takes another function as a parameter and a and b, which are the lower and the upper limits. All the other parameters are optional and you can try them out by yourself. Okay, so here I'll take a variable, say I, and then I'll type SciPy dot integrate dot quad, the name of the function. And the first thing I'll have to do is pass a function as a parameter. So I'll just use a lambda function. So I'll just type lambda of x and I'll compute the exponent of 10 for this x. So I'll type special dot exp of 10, which is the name of the function, and the parameter of this will be x. So this was our first parameter. And now I'll have to pass the lower and the upper limits. So I'll just say 0, 1, and then I'll just print I. Okay, so I hope you all are clear till here. Now let's get back and see how we can solve double integration problems. A double integral, as many of us know, consists of two real variables. To compute this, you can make use of the dbl quad function, which will take the function to be integrated as its parameter, along with 4 other variables which define the limits and the functions dy and dx. So to make use of this function, all I'm going to do is take some variable, say e, and to this, I'll just assign a lambda function, and I'll pass any expression of my choice. So I'll just say x star y far 2. Now I'll take another variable, say f, within which I'll store another lambda function, and to this lambda function, I'll just take one argument. Now I have to define another variable. I'll name it as g, and then a lambda function again. Now I'll just make use of the double integral function. So integrate dot dbl quad, and I'll have to pass the parameters starting with e, and then the limits. I'll just say 0, 2, and then the functions f and g. Okay, so as you all can see, this function has returned the value of the double integral. I hope everyone's clear till here. So now let's get back to our presentation and take a look at some of the Fourier transform functions present in SciPy. Fourier analysis is a method that deals with expressing a function as a sum of periodic components and recovering the signal from those components. To calculate this, you can make use of the FFT function and the IFFT function, which return the discrete Fourier transform and the inverse Fourier transform of a real and complex sequence. So now, let's move on and see how this works. The SciPy subpackage that contains these functions is the FFT pack. So from scipy.fft pack, I'll import FFT and IFFT function. And now I'll just import the NumPy library as NP. Sorry, I made a spelling mistake over here. It's NumPy. And then I'll just take a variable x within which I'll store a NumPy array with some random values. I'll take another variable, say y, within which I'll store the Fourier transform of x. So I'll just say FFT of x and then print x. Sorry guys, I wanted to print y and I printed x by mistake. Okay, so as you can see, I've got a list containing the Fourier transform of x. In case you want to find the inverse of it, all you have to do is use the IFFT function and hit run. Okay, so as you can see, the IFFT function has returned the inverse Fourier transform of x. So I hope everyone's clear till here. In case you have any doubts, please do let me know in the chat box and my team is here to help you. So the next topic that we'll be covering in this session is linear algebra. Linear algebra deals with linear equations and their representations using vector spaces and matrices. SciPy is built on Atlas, LaPack, and BLAS libraries and is extremely fast in solving problems related to linear algebra. In addition to all the functions present in the NumPy library, SciPy also provides a number of other advanced functions. Also, if NumPy is not used along with ATLAS, LAPACK, and BLAS support, SciPy is much faster compared to NumPy. So now let's move on towards our Jupyter notebook and see how to solve linear algebra problems. Okay, the example that I'm taking over here is finding the inverse of a matrix. Mathematically, the inverse of a matrix A is a matrix B such that A star B is equal to an identity matrix. An identity matrix is a matrix consisting of ones down the main diagonal. To compute this, you can make use of the INV function present in SciPy. To do this, I'll just take a variable, say A, and within this, I'll just store a NumPy array, and this time I'm going to create a two-dimensional array. I'll just pass some random values. And I'll store the inverse of A in B. Finally, I'll just print B. Oh, one thing I forgot to do over here is import the submodule. So I'll just type from SciPy, import linalg, and then I'll hit run. Okay, as you all can see, I've computed the inverse of A using the INV function. So now let's get back to our presentation and take a look at the final topic of this session, wherein we'll take a look at the interpolate subpackage of SciPy. In the field of numerical analysis, interpolation refers to constructing new data points within a set of known data points. The SciPy library consists of a subpackage named scipy.interpolate that consists of spline functions and classes, one-dimensional and multi-dimensional interpolation classes, etc. In today's session, I'll be showing y'all how you can solve univariate interpolation problems. Univariate interpolation is basically an area of curve fitting which finds the curve that provides an exact fit to the series of two-dimensional data points. To do this, you can make use of the interp1d function present in SciPy. So I already have a code for this. I'll just copy it and I'll paste it over here. So as you can see, I'm making use of the interp1d function to find x1 and y1 which range between x and y. So all I'm going to do is hit run. So as you all can see, x1 and y1 have been computed between x and y. Okay, so with this, we've reached the end of this session. I hope you've enjoyed and learned something new. Make sure to practice as much as possible. And if you have any doubts or queries, please do let me know in the comment section and I will revert to you at the earliest. Goodbye and take care.